In this video, we're going to talk about single stage experiments, which is really the book's way of kind of introducing us to probability. Okay, so that's what we're going to kind of be looking at for the next chapter. So, what is the probability of something? Well, it is the likelihood that something will occur. Kind of using that same phrase of something. Okay. Um, so I kind of gave some definitions just because there's a lot to go through in this section, and I wanted to kind of speed it up a little bit. So, an experiment is a repeatable process where results are uncertain. An outcome is the phrase we use for a possible event, though we also use the word events. We kind of use those two interchangeably. And the set of all possible outcomes is the sample space. We also have this notation we often use for E representing an event. We usually refer to them as capitals like that so that we kind of understand that we're talking about the event itself. And then the probability of E, we use this kind of throwback to function notation. P parenthesis E is the probability of the event E. Okay, so for each experiment, determine the sample space and the probability of the given outcome. So rolling a six-sided die once and obtaining a two. So in this case, the sample space is referring to the possible outcomes we can have for rolling a six-sided die. And that would be 1, 2, 3, 4, 5, 6. Typically, we use the little squiggly fancy brackets, like look like kind of a sad one, to write the sample space. So we're kind of treating it like a set. And then the probability of obtaining a two, well, that's one outcome out of six. So the probability of two, we would write as 1 out of 6. So notice how I kind of cheated in the way I wrote that probability notation for this particular problem. It makes sense when I'm saying that from the six-sided die, an outcome could be 2. Okay, tossing the coin once and obtaining a head. Okay, so for this one, the sample space is only 2 possible outcomes, and that's heads or tails. Okay, so the possibility of getting heads would be 1 out of 2. Selecting a green marble on one draw from a box containing 5 green marbles and 7 blue marbles. So in this case, our sample space are the marbles, right? So we would have the 5 green marbles and 7 blue marbles. And the way we could do that, by the way, is you could literally list them out. And if I wanted to just kind of do it quickly, I could do green, 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 right? I could list it 5 times and then B for blue, right? 7 times. 2, 3, 4, 5, 6, 7. So if I wanted to actually list out all the outcomes, I could do it this way. Most people are comfortable with going ahead and writing it this way, though this is rare that you're asked a sample space that would kind of look like this. All right, probability of selecting a green would be, well, there's 5 possible greens out of 12 marbles total. Okay, so they actually, what I kind of just said there, 5 possible greens out of 12 marbles total, is kind of a way we're going to look at the formula for finding probability in just a minute. That's going to be on the next page here. Before we do that, we have some more definitions. Experimental probability is the probability that is determined by conducting experiments and observing the results. Now, this phrase conducting experiments doesn't always mean you're running out there and doing something active. Like in the sense that you are forcing something to happen, like rolling a die or flipping a coin or drawing a marble. Experiments could be asking a question of people, like surveying people and getting their response. Okay, that's a possibility as well. So experimental probability could mean that. But in this class, because we're talking about working with an elementary environment, we do tend to think of it as an experiment, you know, flipping a coin 50 times and recording all the results, right? Like that would be something they would kind of look at. So experimental probability comes from data. And they often use simulations to do this. Now, our book does go into discussion about simulations, but we won't really do much of that. We will kind of just kind of talk about it in theory a little bit, and that's about all. Okay, then we have theoretical probability. That's probability based on the ratio of how many ways an event can occur to the total number of possibilities. So when I talked about, what's the probability of getting 2 on a dice, I didn't have to roll a dice to see that. I kind of use the idea, well, there's only one way to get a 2 out of 6 ways total, which leads us to the basic probability formula. The number of ways an event E can occur over the total number of outcomes. So let's focus on theoretical probability. They love the spinners. So we have a lot of examples with this. If you printed your spinner and it's black and white, you may not have these colors. You may want to write down, right? Maybe the left one's yellow, right one's red, blue, and green. Just kind of label them. Okay, so for this given spinner, what is the probability of blue? So in this case, we're kind of looking at the area. Now, we will go ahead and ignore the borders as kind of being negligible, okay? Meaning that they won't have a large enough probability of happening to really stress about them, okay? And we're going to assume this spinner's perfect and that we're able to kind of flick that thing and it has an equal chance of landing in any category. Okay, so in that case then, since blue is taking up about a fourth of this, right? Since they're all equally drawn wedges, it would be probability of blue would be 1 out of 4. And we call this all those probabilities there having an equal chance of occurring. So the probabilities are all, or I should say maybe the colors. Sorry, let me say that a little differently. The colors are all equally likely to occur. So that would mean that all of them have the same probability of occurring if they're all equally likely to occur. All right. Okay, so let's look at it. This spinner, and this time we are asked to find the probability of yellow, probability of green, probability of blue. Okay, so a little bit different this time. All right. To me, though, we're going to kind of, again, just ignore the borders and divide this up. So it definitely looks like yellow is half, right? Like half, I think I'm feeling pretty good about saying that the probability of yellow is 1/2. And green kind of still looks like the one that we just kind of saw above. In other words, if we're kind of thinking of it in 4 sectors, right? This would be sector 1, sector 2, sector 3, and then this one's all sector 4. Great. So I feel like it's reasonable then to say that green is 1/4. And then blue would be half of 1/4, which is 1/8. So exciting. All right. So we can kind of use those areas to set up those probabilities. Okay. So the book kind of made a point of giving you all possible outcomes of rolling 2 die. So I went ahead and included a picture of that here in the notes. So you'll notice there's 36 total, and that's mentioned, of course. And it's kind of organized really nicely for us to see that all of the things in the first column is when the first die is only going to have a 1. If you look along the diagonal, the one way, the diagonal, they're all the doubles, right? 1, 1, this diagonal, 1, 1, 2, 2, 3, 3, 4, 4, right? You're looking along that diagonal, but the other diagonal, actually, those all add up to 7. Like all of those numbers add up to 7. Okay, so it's just kind of a nice way to kind of see patterns in the die. Okay, so let's go ahead and do some questions about probability. What is the probability of obtaining a sum less than 4? Okay, so strictly less than 4, so can't be 4. All right. And when I kind of look up here, to me, it looks like, all right, well, so this is going to qualify. That's going to get up to 3, 3, and that's it. Everything else doesn't work. Okay. So probability of obtaining a sum less than 4 would be 3 out of 36, or 1/12. Okay. Part B. Obtaining a sum of 5. Okay, so this is kind of where the cool pattern kind of plays in here. So this 1/4 is 5, but so is this 2 out of 3, 2 and 3, and then 1/4. So all of these right here along this diagonal add up to 5. So there's 4 of those total out of 36, which reduces to 1/9. Erase that. And then C, obtaining a sum greater than or equal to 9. So this time they can equal 9, but we also are interested in being greater than 9. So basically, if you kind of look at where it's 9, right? So let's see, from here down, right? All of these are 9 or bigger. Okay. And so let's see how many are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 36, which will reduce to 5/18. And there you go. All right. Let's look at flipping a coin 3 times. Let's list the sample space and then determine the following probabilities. Okay, so let's start with the sample space. So when you flip a coin 3 times, I'm just going to go ahead and use H and T to make my life a little bit easier. So you could get heads, heads, heads. You could get heads, heads, tails. And then you can get variations on this, meaning like you could get 1 tail and 2 heads, but maybe the tail happens to be second or first, right? And then you could get 2 tails and then heads. And then all the variations on this, maybe heads came second or first, and then you could get all 3 tails. Okay. Ooh, that's a sad looking squiggle. So there we go. There's our sample space. And then the probability of obtaining exactly 2 heads. Okay, so which ones qualify? Let's see. This works. 2 heads, 2 heads, 2 heads. Exactly 2 heads. So that would be 3 out of 8. Okay, for part B, obtaining at least 2 heads. Okay, so now it could be more than 2 heads. And there's only one that qualifies, and that would be this additional one, because that does have more than 2 heads. So now that's 4 out of 8, or 1/2. All right. So this steps us into probabilities of compound events. So this is kind of where it gets a little bit more complicated. So to do that, we're going to kind of review briefly from section 2.1 when we talked about the union of sets and well, when we talked about sets, really. So the union of sets is when 2 sets, well, let's say members of 2 sets, or all members of 2 sets are combined. Okay. So if set A happens to be 1, 2, 3, and set B happens to be 3, 4, 5, combining A and B, the union, which we use an actual U to represent, would be 1, 2, 3, 4, 5, and of course we don't list 3 twice. We just count it once because it's in both sets. Okay, intersection of sets is the members in common in both sets that these sets have in common. So in our above example, okay, so using the same A and B, To find the intersection, we use an upside down U. And for that one, the one member they have in common is 3. So there we list 3. Disjoint sets are sets that have no members in common. Sets that have no members in common. So that was just some terminology we had talked about to review, because we're going to see that notation again here when we're looking at these compound events. So an outcome is an event A or B if the outcome is in A or is in B or is in both A and B. This is linked to the idea of union between sets, and we can use the notation A union B. Okay, so let's kind of look at how that works in an example. So using the spinner below and the events listed, find the probabilities. Okay, so we have this orange, red, blue, yellow, green, purple. And I want to kind of take a second and notice about what each probability is. Okay, so I'm seeing that this half of the circle, right? It looks like they're all 3 equal. Okay, but it's half of the circle. So that would mean each of these are 1/6 of the circle. So if we kept that wedge pattern continuing, right, it would be 6 pieces total. Okay, well, using that kind of same logic here, this orange piece kind of looks like the red and blue combined, right? So that would be 2/6 or 1/3 of the circle. And this wedge looks like it's having one of the 1/6 wedges. So each of these are 1/12. Okay, so now that we kind of have that, I'm going to list here what we have because of the colors. So the probability of orange is the 1/3. The probability of purple is 1/12. Same with the probability of green. Probability of yellow, red, and blue are all 1/6. And I do want to note, because they all are all possibilities, these should all add up. If we add all these fractions together, it should add up to 1, right? For 100%. Okay. So they do kind of use that idea, and I just want to kind of point that out. Okay, now let's look at the events that we're interested in here. Let me just zoom out a smidge so I can fit it all onto the screen. Okay, obtaining a primary color, which is either red, blue, or yellow. Obtaining a color with 6 letters in the name, obtaining a color with 5 letters, 4 letters, or fewer than 6. Okay, so probability of E union H. Okay, so probability of E, red, blue, or yellow. So basically, we're taking the probabilities of red, blue, or yellow, okay, which would be, let's see, 1/6, 1/6, 1/6 for each of those, all right, and H, which is that it has 5 letters in its name. So which colors qualify for 5 letters in the name? And that would be, let's see. Actually, we could just kind of find these 2 probabilities. That's basically what I'm going to do here. I'm going to find the probability of E and then the probability of H and add them together. And the reason is they have nothing in common, because in E, none of those happen to have 5 letters. So I'm basically going to find the probability of E, which is 1/6 plus 1/6 plus 1/6, which is 3/6 or 1/2. And then the probability of H, here, I'm going to probably go out this way. The probability of H, and here, I'm going to erase these as well, just for the sake of space on my page here, because I have to write so much bigger than you probably have to. So 3/6. So letters that have, colors that have 5 letters in their name. So it looks like it's purple and green qualify. Okay. So, oh wait, no, I'm sorry. Purple does not qualify. Come on, Allison, count the letters, just green. So that would be 1/12. Okay. So when you add 3/6 plus 1/12, let's see, that gives us 7/12 using a common denominator. So E and H are disjoint. They don't have anything in common. Let's look at the probability of T, obtaining a color with 6 letters. Okay, so I happen to know purple works. Let's see, orange also works, and so does yellow. Okay, so for this one, for the probability of T, we're going to kind of total them up. All right, so let's see, what was it? Orange, purple, and yellow. Common denominator would be 12, by the way, right? And that 1/3 would be 4/12 plus 1/12 plus 2/12. So 4 plus 1 plus 2 is 7/12 again. Interesting. All right. Probability of T union K. All right. So for this one, obtaining the 6 letters, union, a color with 5 letters. Okay. So again, we're looking at something that's disjoint. They don't have anything in common. So we're just going to find the probability of T, which we actually already found, and then the probability of K. I'm going to write down that that's what I'm going to do and then actually do it. Okay, so that's 7/12. Okay, now K is 4 letters in the name, and only 2 of those, no, only one of those qualify. That's blue. So that's 1/6. All right. And then when you add that together, so 1/6 is 2/12. So that adds up to 9/12. And then 9/12 reduces to 3/4, which I'm kind of running out of room to write, but I'll just kind of write it underneath. All right. Colors with fewer than 6 letters. Okay, so there's a few that qualify, right? Actually, basically anything but the 6 letters. Okay, so the 6-letter ones were probability of T. Okay, so that was 7/12. So that's going to end up being 5/12. Okay, just so you know, I basically looked at, well, if we're saying that it's fewer than 6 letters, that's basically everything else, because there's nothing bigger than 6 letters listed here. Okay. So I looked at the probability of T, and I'm like, okay, so those are 6 letters. That was 7/12. And I said, okay, well, then what's left over? Well, there's 5 out of 12 left over. But I'm going to show you how to do that without using that approach. That approach, by the way, we're going to talk about in a little while. But what I'll do instead is add up all the colors that are 5 letters or less. So that would be the green, which is 1/12, plus blue, which is 1/6, plus red, which is 1/6. Okay, so those 1/6 are both 2/12. So that's 1 plus 2 plus 2, which is 5/12. Like I said. Okay. Now let's look at an intersection. Took a while for them to do that. So what does E and K have in common? So E is a primary color, K is 4 letters. Okay, so it looks like there's only one that works. That's the blue. Okay, and the probability of blue is 1/6. And I'm putting parentheses, it was the blue one. And now the union of those two now is a little bit different, because now, since we're looking at 4-letter names, so are there any other 4-letter names? No, there aren't. Therefore, what we can do is go ahead and just say that because blue happens to be in the primary color one, combining them together is just going to be primary color one, E, the probability of red, blue, and yellow, period, which we already found to be 3/6 or 1/2. So we're using what's called the addition property, which makes sense since we're adding. All right. In general, the addition property of A or B is the probability of A union B equals the probability of A plus the probability of B minus the probability of what they have in common. If we happen to know up front that A and B are disjoint, meaning they have nothing in common, it ends up just being adding the two probabilities together. Oops. So the only one where technically the in general property, this one would have been used, is part F here. But it happened to be that K, everything that was K was just one, item only, blue only qualified for K. And that happened to be one of the elements that were already contained in E. Okay, the event E. So it kind of made it so we didn't really need to think about this formula here, but we could have if we had needed to. And the way we would have done that, let me just actually pause and say that then, would have been we would have found the probability of E plus the probability of K. Wow, that's not how you draw K. Minus the probability of what they have in common. All right, so probability of E, excuse me, is 3/6 or 1/2, plus the probability of K, we already found that's it's 1/6 because there's only one item and it's blue, minus the probability of E intersect K, which we found in part E, which is 1/6 again. So these two basically end up canceling and we're left with 3/6, which is 1/2. So we could have used that formula, but it happened to be, we were able to reason our way through it. And probability allows you to do that. In fact, a lot of students who tend to kind of be like what I like to term a classic overthinker in life or in math, often do really well in probability because overthinking with probability is actually good and worth it. Okay, now I alluded to this up there as well, and so now we're going to talk about the complement of an event. Complement of an event consists of all outcomes that are not in A. Okay, so two events, if they're complements of each other, that means that their probabilities, or I should say their outcomes, are every other event. So anything in A is going to be left over for B, and they will combine to be every possibility. Okay, so their probabilities will add up to 1. All right, so for example here, S is a common notation used for sample space. So when they label that S, they're saying the sample space is 1 through 6, and let A, the event A, be 1, 2, 3, 4. So the complement of A is 5 and 6. And the probability of A would be 4 out of 6, where the probability of its complement is 2 out of 6. Adding those together would give us 6 out of 6. So using the idea of complementary events, if two fair 6-sided die are rolled, what is the probability of rolling doubles? And then what is the probability of not rolling doubles? Okay, so 2 questions here. Probability of rolling doubles. So you can go ahead and refer back to that picture, and doubles will end up being along the diagonal there. Okay. And so the probability of rolling doubles, let's see, I believe there's 6 along that diagonal out of 36 total, which gives us 1/6. So then the probability of not rolling doubles is basically asking for the complement of this. Okay. And in that case, we kind of think of it as doing 1 minus 1/6. Or in other words, there's 5 out of 6 left over for the complement. Since 1/6 and 5/6 add up to 6 over 6 or 1. Odds. Now, odds are kind of an interesting thing because a lot of people feel like odds are really probabilities and they're not. Odds in favor of an event are saying that the odds are n to m is the ratio of favorable outcomes to unfavorable outcomes. Okay. So when they say the odds on a horse winning are 2 to 3, they mean that 2 times the horse might win and 3 times they wouldn't. Okay. So the probability of that actually needs us to add the two of them together, because we're saying basically that twice the horse wins and 3 times they won't. That means that there were 5 times or 5 races they're taking into consideration. So it's the idea that you would take n and then divide it by n plus m. That's how you'd find the probability. So you have to total the two, the odds that it won't happen. I'm sorry, the odds of favorable plus the odds of unfavorable. Okay, so let's look at an example. One card is selected at random from a deck of 52 cards. Let's determine the following. So let's determine the odds of obtaining or getting an ace. Okay, so if we're going to get an ace, there are, and I mean, if you don't know a deck of cards, I would gladly encourage you go look at a deck of cards, okay, online, but most students are familiar with that, so I won't take the time to discuss it. But the odds of getting an ace, so there are 4 aces in the deck. That leaves 48 non-ace cards. Okay, so the odds are 4 to 48, but you can reduce that as 1 to 12. The other notation used for ratios like this is where you, oops, I'm sorry, you write it with the colons. Typically, they don't write odds as fractions only because they want to encourage you to know that they're not talking about the probability. And a lot of people, like I said, think odds are referring to a probability. Okay, so then let's talk about the probability to get an ace. So the probability to get an ace is 4 out of 52. So we're using the total, or 1/13. Oh, and you should do the reduced form, by the way, whenever you can reduce. The odds of not getting an ace would be 48 to 4, or 12 to 1. Probability of not getting an ace would be 48 out of 52, or 12 out of 13 in reduced form. Okay, and then they like to kind of hit on experimental probability a little bit, and I kind of deviated a tiny amount from the experiments to show you an example of this type of probability, but not really with an experiment, more with data collection. Okay, and I kind of cheated a bit for this, just for our purposes, just so that we didn't have to worry about trying to do simulations. Okay, so here we have a table of information. They surveyed 100 people, organized by gender and whether they are right or left-handed. So male, female, right-handed, left-handed. Okay, so let's, using the denotations M, F, R, L, find the probability of M. So we should probably find the total here. So let's see. 43 plus 9 is 52. And that's 48. Oh, actually, just kidding. We knew the total was 100. Wow, Allison. Okay, it's fine. It's fine. But I needed the totals anyways to kind of answer the first question, which is probability of male. So we actually needed the whole row because all of these people here are male. So therefore, 52 out of 100 are male. I'm going to go ahead and write it as a decimal. Or a percent would have been completely reasonable as well. We use percents a lot for probabilities too. So I think both of these are a reasonable way to answer it rather than reducing the fraction. Okay, right-handed, I should add up the column of right-handed. So let's see, that's going to be 87 out of 100, or 0.87. I'll go ahead and just do it in decimal form. Okay, now intersection of male and right-handed. Okay, so that actually comes right off the table. That would be this group of people right here, because those are 43 people who are male and right-handed. So we are taking 43 out of 100, or 0.43. and then probability of male union right-handed. So that means that we're combining the two together. We're taking all the males, all the right-handed. So we're going to use that formula from earlier. We're going to do the probability of male plus the probability of right-handed, oops, minus the probability of male intersect right-handed, which we already found. Actually, we've already found all these things, right? So we're going to take 0.52 plus 0.87 and minus 0.43. Okay, so here, I'm going to actually do this in my head. I don't have my calculator. So 0.87 minus 0.43, let's see, that's 44 plus 52 is 98. Is it really? Hold on. Now I don't feel so confident about it. So 43, let's see. That's 44.44 plus 0.52. Yeah, it's 96. 96. Okay, wow, that's a lot. And that's because right-handed makes up a huge portion of this group we're looking at, right? By like a long shot. Okay. And therefore, when you're saying that they could be right-handed or possibly male, right? Now you're including a bunch of females who are right-handed and all the males, which are 43 people as well. So really, we're kind of including that. Now, from the table, I can kind of verify my answer here by looking then at all the right-handed people, which were 87 right-handed people, plus the 9 left-handed males. So that does total up to 96. Okay, wow, I feel better about it. And there you go.